Hello, everyone, and welcome. I'm Russ LeBlanc, your personal NEC consultant and code expert. Thank you for joining me. In this video, I'm going to be explaining branch circuit load calculations for fixed multi-outlet assemblies. So if you'd like to grab your 2023 code book, you can follow along. And maybe you want a calculator and a pen or pencil and some scrap paper if you'd like. Okay, let's dive in. All right, we are looking at 220.14h for fixed multi-outlet assemblies. In that section, it says this: fixed multi-outlet assemblies in other than dwelling units or guest rooms or guest suites of hotels or motels, they are calculated in accordance with the following. And there's two provisions there. Provision 1 says this: where appliances are not likely to be used simultaneously, each 5 foot or fraction thereof, each separate and continuous length, are calculated at 180 volt amps. And I want to point out here, this section says appliances. It doesn't say tools or lights, right? It says appliances. It doesn't talk about the receptacles not likely to be used simultaneously. It says appliances might not be used, or it's unlikely to be used simultaneously. So I suppose in this case, appliances could be plugged into every single receptacle, but just not used. Okay, and in that case, the load calc would be 180 volt amps for every 5 feet of multi-outlet assembly. And I'll show you some pictures of that, and we'll look at some definitions for multi-outlet assembly. Let's look at the second provision, 220.14h, paragraph 2. There it says where appliances, and again, appliances, where appliances are likely to be used simultaneously, every 1 foot or fraction thereof are calculated at 180 volt amps. So in this case, every foot is calculated at 180 volt amps, or even a fraction of a foot. And in both cases, paragraph 1 and paragraph 2, that fraction doesn't have to be a major fraction of. It's a fraction of 5 feet, or it's a fraction of 1 feet. Any fraction, not a major fraction. So for example, if I had 1 foot plus 1 more inch, well, that 1 inch is a fraction of 1 foot. So that first 1 foot gets calculated at 180 volt amps, and then that next 1 inch also gets calculated at 180 volt amps, because that's what it says. It doesn't say a major fraction of a foot. In that case, it would be 6 inches, right? So it's 1 foot, and then if it was 6 inches or more, that next 6 inches or more would be calculated at 180 volt amps. That's not what it says. Paragraph 1 doesn't say that, and paragraph 2 doesn't say that. It says any fraction of 5 feet or any fraction of 1 foot, they get calculated at another 180 volt amps. That's what it says. And it also says that the calculation is based only on the portion that actually contains receptacles. So now would be a good time to maybe take a look at a definition. What is a multi-outlet assembly, right? I had a picture at the very beginning. I'll show you some more. There is a definition in Article 100, and it says this: a multi-outlet assembly is a surface, flush, or freestanding assembly with a raceway and fittings or other enclosure provided with one or more receptacles for utilization equipment. Utilization equipment could be appliances, it could be tools, it could be lights. That's all types of utilization equipment. Now, there is an article that covers multi-outlet assemblies. That's Article 380, and there's a whole bunch of rules there about what you can and cannot do with multi-outlet assemblies. We're not covering that today. We're just focusing on these load calculations. All right, in this graphic, there's a very common example of multi-outlet assembly. It's Plugmold, right? Made by Wire Mold. Plugmold, that's a very common type of multi-outlet assemblies. Of course, there are other brands, right, that might make multi-outlet assembly. This one is very common, very popular. It's just with the cover removed, right? So the top section, you see the cover is on, and then the bottom portion there, it's the two sections, right? You have the back that gets mounted to the wall, and then the front portion with the receptacles and the wires that gets kind of snapped in. And this whole thing is then connected to the branch circuit wiring. And you can see the wiring at the end, and that would be where you would connect a fitting that would allow you to connect the branch circuit wires. And I have a picture in the next graphic for that. All right, so you see in the end there, that's the end fitting that will get attached to the multi-outlet assembly, or the plug mold in this case. And that's where the branch circuit wiring would attach to the wiring that's part of the multi-outlet assembly itself. So there are load calculations for these multi-outlet assemblies. And again, it depends on not how many receptacles there are, because you can order these with receptacles very close together and very far apart. That doesn't matter. The only thing that matters is, are appliances used simultaneously or not? Because that changes the load calc. It's either 180 volt amps per foot or 180 volt amps per 5 feet, depending on how appliances are used. Now, the items you see on the graphic here look kind of like multi-outlet assemblies, but they are not multi-outlet assemblies. The one on the left, the black and silver one, that is a plug-in outlet center. That is not covered by Article 380, and there is no load calculation for that. All right, that's portable in nature. And the white one there, that's a relocatable power tap. Also not a multi-outlet assembly, not covered by Article 380, and there's no load calculation for those. Okay, here's again the plug mold, the multi-outlet assembly. Excuse me while I readjust myself, my seat here. Okay. So here's one of the calculations, right? It's depending on if appliances are used simultaneously. And it doesn't matter how many receptacles there are. What matters is, are the appliances used simultaneously? Are more than one appliance used simultaneously, right? Not lights, not power tools, appliances. Maybe it should include things like tools, because you might put this on a workbench, for example. And if you have a bunch of power tools plugged in, well, they're not appliances. So then I guess this wouldn't apply, right? Because they're not appliances. It's only appliances that we have to worry about. And if more than one appliance is used simultaneously, the calculation for that plug mold or that multi-outlet assembly is 180 volt amps for every foot or fraction of a foot. And then the other paragraph says, if only one appliance is used at a time, and again, we're talking about appliances, nothing else, not talking about power tools, not talking about lights, appliances. In that case, if it's unlikely that more than one appliance will be used simultaneously, so only one appliance is used at a time, it's 180 volt amps per 5 feet or fraction thereof. All right, and I want to point out another type of multi-outlet assemblies. They're called Powerpoles. All right, so you see those poles coming down from the ceiling? Those are power poles. At the bottom, there are receptacles. And you'll often see these used in offices that might be wide open, where there's no access to the floor underneath for like a floor type of receptacle. And so the installers might decide to drop power down from the ceiling. They install a power pole, and above the ceiling is at the end of the power pole is a junction box where you can attach the branch circuit wires, and then there's wiring going down the channel to the receptacles installed at the bottom of the power pole. All right, here's another example, right? And that goes from the floor up to the ceiling, this power pole. And only this portion of the multi-outlet assembly, the bottom portion, has receptacle outlets. And so the load calculation is only based on the portion that actually contains receptacles, right? So if that's a 15-foot power pole, for example, we don't use the 15-foot length for the load calc. We only use the portion where the receptacles are actually installed, right? That's it. So you see the part highlighted or outlined there and circled in green. That's the portion you use. So it's 2 feet or 3 feet worth of the power pole or the multi-outlet assembly, right? That's a total different calculation compared to using the whole 15-foot length or the whole 20-foot length, whatever it happens to be. Only the portion that actually has receptacles, that's what you use, right? So the load calculation is going to be much smaller if you don't have to use the entire length. All right, let's do a couple examples. In this example, we're going to say that there is going to be more than one appliance used simultaneously. So in this case, we have to do the math at 180 volt amps per foot or a fraction of a foot. So what's the branch circuit load for 13 feet of this multi-outlet assembly? If you want to take a moment to do that math, you can pause the video and start it back up when you're done, and we'll give you the solution. Okay, here's the solution. Oh, I'm going to have to move my screen here. I see. No problem. Anyways, as I'm recording this, I'm looking at myself and the position of where my video is of myself. I'm going to have to relocate that for this slide because I'm blocking it a little bit. In any case, 180 volt amps per section times 13 sections. That math works out to 2,340 volt amps. Okay, that's the calculated load. Here's another calculation. This is example 2. In this case, we have 13.5 feet. All right, so again, if you want to pause the video here and give it a shot, try to do the math, you can restart the video and I'll give you the solution. Here's the solution. 180 volt amps per section times 14 sections. And again, I'm doing 14 sections instead of 13.5 because every fraction of a section counts as a whole section, right? Every 1 foot section or fraction thereof is 180 volt amps. So the math there works out to 2,520 volt amps. That's how we do the math. Let's do another one. This is example 3. Now we're going to say only one appliance is used at a time. All right, so now it's 180 volt amps for every 5 feet or fraction thereof. And again, it's any fraction thereof. So it's 5 feet, 1 inch. Well, that's 180 volt amps for the first 5 feet and 180 volt amps for the next 1 inch. Because that's what it says. It doesn't have to be a major fraction of 5 feet. Just any fraction of 5 feet counts as another 180 volt amps. Pretty straightforward, as long as you know that, right? Okay, in this case, we're going to say that there are 65 feet of this multi-outlet assembly. And so what's the calculated load in this case, right? And so, again, now only one appliance is being used at a time. So instead of 180 volt amps per foot, it's 180 volt amps for every 5 feet. So we need to know essentially how many 5 foot sections we have, right? Okay, if you want to take a moment and do the math, you can pause the video. And when you're done, you can restart and I'll give you the solution. All right, here's the section, not the section. We have to figure out how many sections we have. Here's the solution. How many 5 foot sections do we have, right? Because every 5 foot section or fraction thereof is calculated at 180 volt amps. So we need to know how many 5 foot sections we have. There are 13, right? 65 feet divided by 5 feet per section, that's 13 sections. Every 5 foot section or fraction thereof is 180 volt amps. So the load looks like this. The load gets calculated at 180 volt amps per section times 13 sections. That's 2,340 volt amps. Pretty straightforward. Let's do another one. This is example 4. Still only one appliance being used at a time, regardless of how many receptacles there are and how far apart they are. It's 180 volt amps for every 5 feet or fraction thereof, if only one appliance is getting used at a time. What's the branch circuit load for 68 feet of this multi-outlet assembly? Again, we need to know how many 5 foot sections because each one of those is calculated at 180 volt amps. So we have to divide the total length by 5 feet, or 5 feet per section. 68 feet divided by 5 feet per section, that's 13.6 sections. And then the load is calculated at 180 volt amps per section. Well, we're going to say there's 14 sections because there's 13 sections and then a fraction of a section. So every fraction of a section, every fraction of a 5 foot section is calculated at 180 volt amps. So the math looks like this. 180 volt amps per section times 14 sections, essentially 2,520 volt amps. That's how that math works out. One more example. Still sticking with this only one appliance being used at a time. What's the branch circuit load for 66 feet of this multi-outlet assembly? Here's the solution. Again, before I put it up, if you want to pause the video, you can try to do the math and then restart the video. First, you want to figure out how many 5-foot sections we have, right? That's the first thing. How many 5-foot sections? Each one of those is 180 volt amps per section, or fraction thereof. 66 feet divided by 5 feet per section, that's 13.2 sections. And remember, every fraction of a section is calculated as a whole section. 180 volt amps. Every full section or fraction of a section is 180 volt amps. So the math works out like this. 180 volt amps per section times 14 sections, 2520 volt amps. That's how we do that math, right? Every fraction of a section is counted as a whole section. Even though it's only 0.2 sections, 13.2 sections, you just round up. You always round up. If you have any fraction of a section, you just round up to the next whole number when you're doing these load calcs. All right, let's do one more. This is example number 6. How many 120 volt, 20 amp branch circuits are needed for 85 feet? All right, so now we're calculating how many branch circuits we need versus just doing the load calculation. How many branch circuits do we need? If you would like to do the math, you can pause the video, restart it when you're ready, and I'll give you the solution. We still want to figure out how many 5-foot sections, right? So take the total length, divide by 5. That'll tell us how many sections. In this case, we have 17 5-foot sections. Every section or fraction thereof is calculated at 180 volt amps. So the load looks like this, 180 volt amps per section. We have 17 sections, so multiply by 17. The load is 3,060 volt amps. That's the load calculation. Now, the circuit looks like this. The circuit can provide 120 volts at 20 amps. So that provides 2,400 volt amps per circuit. And we're going to divide this load, 3,060 volt amps, across those branch circuits, each at 2,400 volt amps. So take the load, divide by the volt amps per circuit, and that'll tell you how many circuits you need at a minimum. So the load is 3,060 volt amps divided by 2,400 volt amps per circuit, 1.275 circuits. Now we're going to have to round up because there's no such thing as 0.275 of a circuit breaker, right? It's either a whole circuit breaker or it's nothing. So we can't have just one circuit breaker. We need two. We need 2 circuit breakers. 2 circuits are needed, and that is per 210.11a. The minimum number of branch circuits is based on the load calculation in addition to the rating of the branch circuits, right? And so that's what we did there. We did the load calculation, and then we also used the rating of the branch circuits to calculate the minimum number of branch circuits, which in this case is 2. And one more. In this case, we're going to say we have more than one appliance being used simultaneously. So now the load calc is 180 volt amps per foot or fraction of a foot. All right, so we want to calculate the load and also figure out how many branch circuits we might need. So how many 120 volt, 20 amp branch circuits are needed for 85 feet of this stuff? If I have 85 feet of this multi-outlet assembly, excuse me, and that could be in the form of what you see on the screen. It could be Powerpoles. It could be a combination of the multi-outlet assembly on the screen and Powerpoles, possibly all on the same branch circuit. Again, only using the portion of where the receptacles really are, like not the whole power pole, just the bottom portion, the bottom couple feet where the receptacles are actually installed. That's how we do the math, okay? If you want to pause the video, you can stop it here, restart it. After you find an answer, I'll give you the solution. Okay, first we want to do the load calc, right? 180 volt amps per foot times 85 feet. The total calculated load is 15,300 volt amps for all of this multi-outlet assembly. 85 feet worth of multi-outlet assemblies. How many branch circuits do I need to feed that? That's what we're trying to figure out, right? So now we need to know information about the circuit. Here's the circuit information. It's 120 volts, 20 amps. So each circuit provides or can accommodate 2,400 volt amps of load. So we need to take the total VA divided by the VA per circuit, and that'll tell us how many circuits. And there we go. There's the load, 15,300 volt amps. That's the calculated load divided by the volt amps per circuit. We're going to need 6.375 circuits. Well, it's an all or nothing proposition. It's either 6 circuits or it's 7. You can't have less than 6.37 circuits, so you're going to need 7. 7 circuits minimum. And that would comply with 210.11a, which again says the minimum number of branch circuits is based on the load calculation and the rating of the branch circuits. Hopefully you enjoyed that. As always, if you need more information or if you would like to contact me for anything, visit me at russleblanc.net. There's some cool links you might find helpful, and there's also a contact page if you'd like to contact me with any code questions or ideas for a video. See you in the next video.